Good morning and welcome to this seventh lecture of the course Stochastic Hydrology. In the last lecture, you can recall now that we discussed the exponential distribution, the gamma distribution, and we introduced the extreme value distributions. If you recall, the exponential distribution is generally used when we are interested in the time between two critical events. Let us say the time between two flood events, which itself is a random variable, then we would be generally using the exponential distribution. The gamma distribution is in fact a family of distributions, and you recall that exponential distribution is in fact a special case of gamma distribution, where we put eta is equal to 1 in the gamma distribution PDF to obtain the PDF of exponential distribution. The gamma distribution is typically used for rainfall distributions across several time frames. In many cases, we use the gamma distribution also for seasonal rainfall, monthly rainfall and so on. Then we went on to discuss the extreme value distributions. If you recall, we introduced three types of extreme value distributions. They are called as type 1, type 2 and type 3 extreme value distributions. The extreme value distributions are very commonly used in hydrology, because we would be interested often in the peak flows or the minimum flows, the high intensity rainfalls, for example, the maximum intensity, daily intensity of the rainfall, and also the low flows when we are interested in water quality or drought phenomena and so on. Now, the extreme value type 1 distribution, as you recall, is a distribution which draws from a parent distribution which is unbounded in the direction of the extreme values that we are interested in. For example, if you are interested in the maximum values, then it should be unbounded on the positive side. If you are interested in the minimum values, it should be unbounded on the lower side. So, extreme value type 1 distribution essentially comes from the parent distributions which are unbounded on in the direction of the extreme values that we are interested in. And we introduced the Gumbel's extreme value distribution. We will recall, we will review what we discussed in the last class in the first two slides of today's class. The extreme value type 2 distribution is not very commonly used in hydrology. So, we then go on to discuss the extreme value type 3 distribution, which is derived from the parent distribution which is bounded in the direction of the extreme value that we are interested in. For example, if we are interested in the minimum values, it should be bounded on the lower side. So, that we will introduce in today's class, the extreme value type 3 distribution. So, if you recall, we discussed the extreme value type 1 distribution in the last class, which is also called the extreme value Gumbel's extreme value distribution. So, commonly in the hydrology literature, we find this nomenclature, that is Gumbel's extreme value distribution or simply Gumbel's distribution. So, we introduced this PDF in the last class, f of x given by this expression. It has two parameters, alpha and beta, and we have the relationships for alpha and beta, which are estimated from the samples using the standard deviation and the mean. So, if we are looking at the extreme value distribution type 1 for maximum values, then we use the negative sign here in the PDF, and for minimum values we use the positive sign in the PDF. Correspondingly, the parameter beta, the estimate for the parameter beta, we use the negative sign here. It turns out to be mu minus 0.45 sigma for the maximum values, and for the minimum values you get mu plus 0.45 sigma. So, given the sample values, you estimate the sample estimate for the standard deviation, and you also get the sample estimate for the mean, from which you can estimate alpha and beta. We used a transformation y is equal to x minus beta over alpha, which simplifies the PDF, and we write the PDF for the transformed variable y as follows: f of y is equal to exponential minus plus y minus exponential minus plus y, and again minus is used for minimum values in the case of our earlier expression, and plus is used for the maximum values. I am sorry, the other way around. So, we use the maximum, we use the negative value for the maximum value and positive values for the minimum values. So, when we take the CDF, we consider the CDF, you get f of y is equal to exponential minus y. So, this is a convenient form to use for maximum values, and for the minimum values it comes out to be 1 minus exponential y for the minimum values. So, as you can see, it can be written as e to the power minus y. So, this is called as the double exponential distribution. So, when we use the transformation y is equal to x minus beta over alpha, the CDF comes out to be in an elegant form e to the power minus y for the maximum values. Let us consider an example now for the Gumbel's extreme value distribution. If we are looking at the positive extreme value, which means the peak floods or the peak runoff and so on, we will take this example which demonstrates the positive extreme values. The annual peak flood of a stream, it is known that it exceeds a value of 2000 meter cube per second with a probability of 0.02, and it exceeds a value of 2250 meter cube per second with a probability of 0.01. So, these are known from the samples, and then we need to obtain the probability that annual peak flood exceeds 2500 meter cube per second, assuming of course, that the peak flood follows a Gumbel's extreme value distribution. So, how do we do this? So, like we did with all earlier distributions, we first estimate the parameters alpha and beta. To estimate the parameters, we consider the fact that probability of x being greater than or equal to 2000 is given to be 0.02, from which you write probability of x being less than or equal to 2000 as 0.98, and you know that f of y, which is a CDF, is e to the power minus y if we use the transformation. So, we use the transformation and write e to the power minus y is equal to 0.98 for that particular value of y. So, we write this as e to the power minus y is equal to 0.98, and therefore, e to the power minus y by taking logarithms turns out to be minus log 0.98, from which we write y is equal to minus log of this particular term, which is minus log 0.98, from which you get y is equal to 3.902. What is y? You recall that y is a transformation like this, y is equal to x minus beta over alpha. So, this is the y value, which is 2000, which is the particular x value that we are talking about, minus beta over alpha. So, that should be equal to y, which is 3.902. This is the first condition that we generate. Then from the second condition, which is given as probability that the peak flows exceed 2250 meter cube per second is 0.01. So, we write probability that x is greater than or equal to 2250 must be equal to 0.01, from which we write probability of x being less than or equal to that particular value will be equal to 1 minus of this is equal to 0.99. Again we use the same method and then estimate y. So, y in this case turns out to be 4.6, which is y, as you know, is a transformation x minus beta over alpha. So, 2250, which is a particular value of x, minus beta over alpha, this should be equal to 4.6. So, we generated two conditions. We solve these two equations to get the two unknowns alpha and beta. So, we get alpha is equal to 358 and beta is equal to 603. So, like in any earlier distributions, the first step is always to estimate the parameters from the sample values. So, we estimated here in this particular case alpha is equal to 358 and beta is equal to 603. Now, we are asked the question probability, what is the probability that x will be greater than or equal to 2500 meter cube per second. So, this we write it as equal to 1 minus probability of x being less than or equal to 2500, which from the expression for f of y we write it as 1 minus exponential minus 5, that is 1 minus e to the power minus e to the power minus 5, where y is equal to x minus beta over alpha and x is that particular value which in this case is 2500, beta we have estimated it to be 603 and alpha we have estimated it to be 358. So, we get the corresponding value of y as 5.299. So, we write probability of x being greater than or equal to 2500 as equal to 1 minus exponential minus y, which is 1 minus exponential minus y, which is 5.299. So, this turns out to be 0.005, that is probability that x being greater than or equal to 2500 will be 0.005, which is a fairly low probability. Then we move on to what we call as the type 3 distribution. If you recall, the type 3 distribution is bounded on the side of the extreme value that we are interested in. For example, if you are interested in the minimum values, then it should be bounded on the lower side. If you are interested in the maximum values, then it should be bounded on the higher side. Unlike the type 1 distribution, which will be unbounded, the parent distribution will be unbounded in the case of type 1 distribution on the side of the extreme. So, the extreme value type 3 is bounded, is derived from a parent distribution, which is bounded on the side of the extreme in which we are interested in. Now, for the minimum values, if we are considering the type 3 distribution for the minimum values, this is referred to as the Weibull distribution. So, whenever we say it is a Weibull distribution, we are talking about the extreme value type 3 distribution when we are considering the distribution for the minimum value. So, for the minimum values, the PDF is given by f of x is equal to alpha x to the power alpha minus 1, beta to the power minus alpha, exponential of minus x by beta to the power alpha. So, this has two parameters alpha and beta, and this is defined for x non-negative, x greater than or equal to 0 and alpha and beta both positive. From this you can derive the CDF, the cumulative distribution function, as f of x is equal to 1 minus exponential minus x by beta to the power alpha. Now, it can be shown that the mean and the variance of this distribution defined as given here will be the mean is, which is the expected value of x, is beta into gamma function of 1 plus 1 over alpha. Similarly, the variance sigma square is given by beta square into brackets the gamma function of 1 plus 2 by alpha minus the gamma function the square of 1 plus 1 by alpha. So, given the sample values, we should be able to estimate alpha and beta by using these two moments mu and sigma square. Now, if the low bound on the parent distribution is not 0, then we put a displacement epsilon. So, we add a displacement and then redefine our PDF. So, whenever we do not have the lower bound to be 0, then we add the displacement corresponding to the displacement that the parent distribution has, and this is known as 3 parameter Weibull distribution. And associated with this, we have the CDF as given by this expression f of x is equal to 1 minus exponential minus x minus alpha x minus epsilon divided by beta minus epsilon raised to the power alpha. Just compare this with our earlier CDF, where we had 1 minus exponential minus of x by beta. So, all we have done is we have subtracted a displacement factor, displacement parameter x minus epsilon t here and beta minus epsilon here. That is all the difference, and this is called as the 3 parameter Weibull distribution, because it has an additional parameter of epsilon apart from the 2 original parameters alpha and beta. Now, in this case again the moments, that is the first moment mu is given by epsilon plus beta minus epsilon gamma function 1 plus 1 over alpha, and the variance, which is the second moment about the mean, is given by beta minus epsilon square and gamma function of 1 plus 2 by alpha minus the gamma function the square of 1 plus 1 by alpha. So, again from the parameter from the sample estimates of mu and sigma square, you should be able to get the parameters alpha and beta by using also the third moment in that particular case, if we have 3 parameters. We will discuss the parameter estimation hopefully in today's class of different distributions, the methods of parameter estimations. So, Weibull distribution with the 2 parameters alpha and beta appear something like this. As we discussed in the case of gamma distribution, the alpha parameter determines the shape of the distribution. For example, for a given beta, beta is equal to 1. If you change the alpha, the shape will change. Alpha is equal to 1 provides this particular shape. For beta is equal to 1, if you change the alpha, it provides this particular shape. So, alpha governs the shape of a parameter, shape of the distribution, and beta governs the scale of the parameter. For example, for alpha is equal to 2, you have alpha is equal to 2 here, alpha is equal to 2 here, beta is equal to 1 gives you this scale, and beta is equal to 3 gives you this scale. So, alpha is therefore called as the shape parameter and beta is called as the scale parameter. Let us consider an example. We have remember when we are talking about the minimum values, that is the extreme distributions for the minimum values, we call it as a Weibull's distribution. So, Weibull's distribution we are always talking about the lower extreme. So, we will obtain the probability of x being less than or equal to 0.1 using Weibull distribution for a sample x is equal to as given here. Now, these may be low flows in a stream, and we are interested in the distribution of the low flows, and we are interested in the probability that x is less than or equal to 0.1. As I mentioned earlier, interest often exists in low flows when we are talking about water quality or when we are talking about drought situation, where the water availability is of concern, and therefore, we will be interested in probability of the flows being less than or equal to a certain value 0.1. So, these are all the low flows, maybe the minimum annual flows and so on. Now, when we take the mean of this, the sample mean is 0.25. This is simply the mean, the estimate of the mean here, that is the arithmetic average x bar by n, and the sample variance S square is 0.05782. Now, we use these two and equate them to the mean as obtained for the Weibull distribution and the variance as obtained for the Weibull distribution. So, this is in fact called as method of movements, which we will introduce in today's class subsequently. So, essentially what we are doing is the mean as obtained from the sample or as estimated from the sample and the variance as estimated from the sample are equated to the mean as obtained from the theoretical distribution and the variance as obtained for the theoretical distribution, and thus we generate two equations and solve for the two unknowns alpha and beta. So, mean as obtained from the theoretical distribution, as was given here earlier for the 2 parameter Weibull distribution, the mean is given by beta into gamma function of 1 plus 1 by alpha, and the variance is given by sigma square is equal to beta square into brackets the gamma function 1 plus 2 by alpha minus gamma square 1 plus 1 by alpha. So, these are the expressions that we use and then obtain the two conditions. Mu is equal to expected value of x is equal to beta into gamma function of 1 plus 1 by alpha, which is equal to, we write mu is equal to beta into this 1 plus 1 by alpha, the gamma function. Recall that when we introduce the gamma function in the gamma distribution, we said gamma function of 1 plus eta can be written as eta root eta. So, that is the relationship that we use here and then write it as beta into 1 by alpha root 1 by alpha, which turns out to be beta divided by alpha root alpha, or we write it as alpha root alpha is equal to beta by mu from this expression. Then we also use the variance sigma square, which is given by, for the Weibull distribution, sigma square is given by beta square into the gamma function 1 plus 2 by alpha minus gamma square 1 plus 1 by alpha. Again this 1 plus 2 by alpha, we write it as 2 by alpha root 2 by alpha. So, we have taken out beta square and then this is the first term, gamma function of 1 plus 2 by alpha, we write it as 2 by alpha root 2 by alpha minus the gamma function square 1 plus 1 by alpha. Recall that we wrote mu is equal to beta into gamma function of 1 plus 1 by alpha. So, mu by beta we write it as gamma function of 1 plus 1 by alpha, and therefore, the gamma square 1 plus 1 by alpha we write it as from here mu square by beta square, and from there you get sigma square is equal to 2 root 2 mu b. This is what we are writing now, 2 root 2 mu beta minus mu square when you simplify this, and then we get beta is equal to 0.1702 when you substitute the value for mu as well as sigma square. This is mu square and this is sigma square. So, once you get beta, you go to alpha root alpha is equal to beta by mu and get alpha is equal to 0.774. So, this is how we obtain the two parameters. What we did here, we essentially equated the first moment as estimated from the sample, which is the arithmetic average, to the first moment as obtained from your Weibull distribution, theoretical Weibull distribution, and similarly the second moment about the mean, which is the variance, we get the sample estimate and equate it to the second moment about the mean, which is the variance as defined for your Weibull distribution, theoretical Weibull distribution, and thus generate two equations and obtain the parameters alpha and beta. This is in fact called as the method of moments for estimation of the parameters. This we will be introducing in today's class subsequently. So, once you get alpha and beta, the Weibull distribution is completely defined, and therefore, we can talk about the probabilities associated with the random variable following the Weibull distribution. So, we write probability of x being less than or equal to 0.1, which is by definition equal to f of 0.1, capital F of 0.1, and f of x for the Weibull distribution is given by 1 minus exponential minus x by beta to the power half. This x is that particular value of x that we are interested in, which is 0.1 in this case, and beta is estimated here as 0.1702 and alpha is estimated here as 0.774. So, we substitute these values and get f of 0.1 is equal to 0.4845, or probability of x being less than or equal to 0.1 is 0.4845. So, essentially in the extreme value distributions, what we do is that we use either the type 1 distribution or the type 3 distribution, depending on whether you are interested in the lower extreme or the higher extreme. Now, the type 1 distribution essentially comes from the parent distributions which are unbounded on the side of the extreme that you are looking for. For example, if you are looking for the minimum values, then the parent distribution which has a lower bound or the lower extreme unbounded. For example, the normal distribution which has a lower extreme unbounded. If you are interested in type 1 distribution which and you want to use the maximum values or the higher extremes, then the parent distribution should have a higher bound, which is the bound on the right side should be unbounded. Again, the normal distribution is an example, or the log normal distribution is an example, gamma distribution is an example, which have the higher bound as unbounded. We use the type 3 distributions when we are looking for, let us say, minimum values, and the parent distribution has the lower bound bounded. So, in the type 1 distribution, type 3 distribution, we are talking about the parent distribution being bounded on the side of the extreme that we are looking for. When we are using the type 3 distribution for the minimum values, it is called as the Weibull distribution, which is more commonly used in hydrology for events like low stream flows, low rainfalls, minimum temperatures and so on. So, when we are looking at the minimum values or the lower extreme values, then we use the Weibull distribution. So, essentially in hydrology most commonly we use the type 1 distribution for the maximum values, typically the flood peaks and high stream flows, high intensities of rainfall and such higher values of the event, higher values of the particular random variable. We will be using the type 1 distribution, which is also called as the Gumbel's distribution. And the type 3 distributions we typically use in hydrology for the lower bound of the random variables, typically for low stream flows, minimum rainfall, minimum temperatures and such events, and this is also called as the Weibull distribution. So, we have covered a range of distributions. We started with the normal distribution, then we went on to the log normal distribution. The normal distribution is most commonly used in for normal processes, for example, average stream flows, average annual stream flows, seasonal rainfall, where you are accumulating over large periods of time. Such normal events we use normal distribution, it is most commonly used in hydrology. But the limitation of the normal distribution, if you recall, are limitations are that there is a finite probability associated with negative values, and often in hydrology we deal with non-negative values, non-negative variables. For example, stream flow cannot be negative, rainfall cannot be negative and so on. Also, the normal distribution is a perfectly symmetrical distribution, and in hydrology we often get situations where the distributions are not symmetrical and they are often skewed distributions. It is in this situation that the log normal distribution has advantage, that it is defined for non-negative values of x. So, we graduated onto the log normal distribution, where we are talking about a positively skewed distribution, and it is defined essentially for non-negative values of the argument x. Then we also went on to the exponential distribution, which is typically used for time between two critical events, and then we introduced the gamma distribution, which is a family of distributions of which exponential is a specific case. Then we went on to introduce the extreme value distributions, when we are interested in really high values or low values of a particular random variable. Now, these are some of the distributions that we commonly use, but they are not an exhaustive set of distributions. As you can recall, any function which satisfies the two conditions, namely f of x is non-negative and the integral between minus infinity to plus infinity of f of x with respect to x must be equal to 1. Any function that satisfies these two conditions is a potential probability density functions. So, there are virtually infinitely many such probability distributions. We have in this particular course introduced only those distributions which are commonly used in hydrology at first level. Now, we move on to another topic where we are interested in estimating the parameters of a distribution. So, as we know, any distribution which satisfies those two conditions that I just mentioned is a potential distribution, and therefore, we have virtually infinitely many such distributions. Each distribution will have certain parameters. For example, the normal distribution had 2 parameters, and the Weibull distribution that we just introduced had 2 parameters alpha and beta. The exponential distribution had a parameter lambda. The gamma distribution had 2 parameters, log normal distribution had 2 parameters, and so on. So, typically a distribution will have one or more than one parameters. Given a sample, we should know how to estimate the parameters from the sample, parameters of a distribution from the sample. For example, you have a sample of observed stream flows for the last 50 years. How do we make use of this sample of observed stream flows to estimate the parameters of, let us say, normal distribution, assuming that this sample follows a normal distribution, or if it follows a let us say exponential distribution. If we have a sample of time between 2 critical events and we have collected that sample over the past historical period, how do we estimate the parameters of the exponential distribution, assuming that the sample follows the exponential distribution. So, we now introduce the important topic of parameter estimation. So, essentially the problem that we will be concerned with in parameter estimation is that you have a sample of observed values, and from this sample we want to estimate the parameters of a particular distribution. So, how do we go about this? So, first we introduce the concept of the parameter estimation itself. We have been talking about the PDF and the CDF. We denoted the PDF by f of x, small f of x, and the CDF by the capital F of x. But in general, f of x and f of x, the small f of x and the capital F of x are also functions of the parameters, and therefore, we should be writing f of x semicolon theta 1, theta 2, etcetera, theta m. So, this has m parameters. Similarly, f of x has m parameters theta 1, theta 2, etcetera, theta m. Now, we want to estimate these parameters theta 1, theta 2, etcetera, theta m from an available sample x 1, x 2, etcetera, x n. So, this is an observed sample. From the sample, we should be able to estimate the parameters theta 1, theta 2, etcetera, theta m. The theta 1, theta 2, theta m, which are the set of parameters, which is a set of parameters, is in fact a function of the sample itself, because you are estimating. I repeat that theta 1, theta 2, theta m, etcetera, are the parameters of the population, and you are estimating from the sample the associated parameter estimates. You are obtaining the associated parameter estimates theta I cap. So, whenever we put a cap here, it means that it is an estimate. So, we denote, for example, theta I cap as an estimate of theta I. Whenever we are talking about the estimates will be a function of the sample itself, and therefore, as you change the sample, you get a different estimate, and therefore, the theta I cap is a function of the sample, and because this sample is a random sample, theta I cap itself becomes a random variable. That means, you are estimating these parameters, and these parameter estimates themselves become random variables with their own probability distributions, their own moments, and so on. So, theta I cap has its own distribution and therefore, its own moments. For example, it has its own expected value, its own variance, and so on. So, the question is, what are the best estimates from the available samples sample x 1, x 2 etcetera x n, which in some sense is best for our purpose of using this particular distribution f of x. Now, we introduce two important properties of the estimators. Estimates or the estimators, we use them synonymously. So, we have one property called as unbiasedness of the estimate, or we call them as unbiased estimates, and we have the property of consistency of estimates, or we call them the associated parameter estimates as consistent estimates of the parameters. Let us look at what we mean by the unbiasedness or unbiased estimates. As I just mentioned, the theta cap, which is a parameter, is itself a random variable, and the expected value of theta cap, if it approaches theta, that is, we say expect an estimate theta cap of a parameter theta is said to be unbiased if the expected value of theta cap is equal to theta itself, and the bias, if any, is given by expected value of theta cap minus theta. So, what we are saying here is that your theta cap is such that the expected value of theta cap is equal to theta. This does not mean that an individual theta cap that you get, an individual estimate theta cap that you get will be exactly equal to theta or even close to theta. It just means that the average of many independent estimates of theta will be equal to theta. This is what is meant by a unbiased estimate. Similarly, we introduce the concept of a consistent estimate. Now, an estimate theta cap of a parameter theta is said to be consistent if the probability that theta cap differs from theta by more than an arbitrary constant epsilon approaches 0 as the sample size approaches infinity. So, let us say you have a sample of 50 values and you estimate theta cap, and then you have a sample of 100 values, then you estimate theta cap, and so on. So, as the sample size keeps on increasing, if your probability of theta cap being close to theta with a distance of epsilon, if this probability starts approaching 0, that is probability of theta cap minus theta, the absolute value of this being greater than or equal to an absolute arbitrary value epsilon. If this approaches 0 as n tends to infinity, n is the sample size, as the sample size approaches infinity, then such an estimate is called as a consistent estimate. What we mean by this is that let us say we estimated a parameter theta cap with 50 values with some sample value, and this probability is this particular probability is some certain value, and then as you increase the sample size, this probability becomes lower, increase the sample size again, the probability becomes much lower, and so on. So, as the sample size increases, the probability, this probability starts becoming closer to 0, then it is called as a consistent estimate. However, in certain situations it may so happen that as your sample size is increasing, the estimates that you are obtaining will lead to these probabilities fluctuating around 0, not necessarily approaching 0. Sometimes if they approach 0, sometimes they go away from 0, etcetera, they will become inconsistent estimates. So, in certain situations we will be interested in both unbiased as well as consistent estimates, and therefore, it is important for us to understand this concept and then test for unbiasedness as well as consistency of estimates. Now, having introduced the concept of parameter estimates, we will now look at some methods which are available for estimating the parameters. We will typically use method of matching moments, method of matching points, method of movements, and the method of maximum likelihood. We will introduce these three methods for estimating the parameters. There is also a method of graphical plotting, which is a really approximate method which is used really as a first cut rough estimates, but we will not deal with that particular method in this course. With the computers available etc., it is a method of the graphical method is almost outdated now. In the method of matching points, what we do is essentially we look at the sample values. From the sample values, we estimate certain probabilities as a relative frequency or some such thing, and then we equate these probabilities with the probabilities as expected from the particular distribution, and then from the associated probabilities we obtain the parameters. This is not a very commonly used method. However, when you have samples from which we can estimate, let us say, probability of x being greater than or equal to a given value is 80% and so on. When you can estimate those things as a first cut estimates of parameters, you can use this. It is a simple and approximate method. Let us take an example here. A data set is assumed to follow the exponential distribution f of x is equal to c e to the power minus c x. Now, from the data set that is available with us, we see that 80% of the values are less than 1.5. So, we use this fact to estimate the parameter c. So, what is it that is given? Probability of x being less than or equal to 5 in this particular case. This is written as 1.5, this is written as 5 here, it is actually 1.5. So, probability of x being less than or equal to 1.5 is given as 80%. So, here we are saying this should have been 1.5. So, probability of x being less than or equal to 1.5 is 0.8, because 80% of the values are less than 1.5. Then from this we write, you know that f of x for there is a capital F of x for the exponential distribution. Recall that it is 1 minus e to the power minus lambda x. In this particular case, lambda is c. So, we write this as 1 minus e to the power minus c into x, x is 1.5, this is equal to 0.8. So, e to the power minus 1.5 c is equal to 0.2, from which you get c is equal to 1.073. So, essentially what we did here is that we looked at the sample, we estimated some probability from the sample. So, we said that 80% of the values are less than 1.5, we use that fact and then obtain c. This is one way of estimating the parameters. However, as I said, we just used one of the facts from the sample, that 80% of the values are less than 1.5 and we obtained c. This may be quite an approximate way of estimating the parameters. So, this may not be really the parameter estimate that will emerge from large sample values, where we use the methods of moments or method of maximum likelihood, which we will introduce just now. A better way of estimating the parameters and one of the most commonly used method is by using the method of moments, is the method of moments itself. So, what we do here is that let us say a particular distribution has m number of parameters, theta 1, theta 2, etcetera, theta m. We equate the sample moments. Recall that the first sample moment is the sample estimate of the first moment is the x bar, and similarly the second sample estimate the sample estimate of the second moment is s square, or the variance estimate of the variance, and so on. So, from the sample we can obtain the sample estimates of the moments, first moment, second moment, third moment, and so on. We equate these with the moments obtained on the population or the moments of the theoretical distribution, and then equate them, generate m number of equations by equating the m moments of the sample with the m moments of the population, generate m number of equations, solve these m equations to obtain the m parameters. So, this actually results in m equations, and we solve the m unknown parameters of the distribution. So, again we will take the example of the exponential distribution. So, we have a single parameter lambda here. So, we take the first moment. So, first moment is of this distribution is mu is equal to 0 to infinity, because x is greater than 0 here, 0 to infinity x f of x dx. So, x into lambda e to the power minus lambda x dx. So, we use the we integrate this by using method of separation, and then we get mu is equal to 1 by lambda. So, this is 0 to infinity. Essentially what we are doing here is you are using the fact that you are integrating u v is equal to u v dash minus integral v u dash, that is what you are using here, and then you simplify that and get mu is equal to 1 over lambda for 0 to infinity. This is fairly straightforward, you can refer to this later. So, mu is equal to 1 over lambda. Now, what is the sample estimate of mu? Mu is the first moment. So, if you have a sample, how do we estimate mu? From the sample we estimate it by x bar, which is the arithmetic average. So, we write this as x bar is equal to 1 by lambda, and therefore, lambda cap, which is the sample estimate of the parameter lambda, will be equal to 1 by x bar. So, this is how we proceed for a distribution having any number of parameters. If you have 2 parameters, what would you do? You will take 2 moments, first 2 moments. One is the mean, and the second one is the second moment about the mean itself, which is a variance. And then you equate it to the sample estimates of these corresponding moments, and then obtain 2 equations, solve for the 2 equations, and then obtain the 2 parameters. So, let us look at one other example here, which has again a single parameter theta. So, f of x is equal to theta sin square x for x varying between 0 and pi. You can verify that this in fact is a valid PDF by integrating this between 0 and pi, you will get 1. So, this has one parameter theta. So, again we will take the first moment. So, the first moment of this would be 0 to pi x into f of x, which is theta sin square x dx. So, again we integrate by parts, you get you can either use MATLAB or you simply integrate it by parts. You will get x bar is equal to theta sin x square by 4 minus x sin 2 x by 4 plus x square by 4 between 0 and pi. So, that turns out to be x bar is equal to theta pi square by 4. Remember here we said x bar is an estimate for mu, and therefore, we get theta cap here. This will be theta cap. So, theta cap will be 4 x bar by pi square. So, the method of moments, we take those many moments as we have the number of parameters and generate those many equations from these and equate and obtain the associated parameters. Now, we introduce a slightly more rigorous way of estimating the parameters, which is the method of maximum likelihood. We have the sample consisting of n values x 1, x 2, etcetera, x n. Now, your f of x, if we write it for x 1, x is equal to x 1, x is equal to x 2, etcetera, then we define a likelihood function as f of x 1 theta 1 theta 2 etcetera theta m into f of x 2 theta 1 theta 2 etcetera theta m into f of x n theta 1 theta 2 etcetera theta m and so on. The basis of this is that is you write it for n terms here. So, this so on for n terms. The basis for this is that the once a sample has occurred x 1, x 2 etcetera are independent. So, we are looking for those set of parameters theta 1, theta 2, etcetera, theta m, which will maximize the likelihood of this sample x 1, x 2, etcetera, x n appearing from that particular PDF. So, in essence we are writing it as a joint distribution of f of x 1, f of x 2, f of x 3, etcetera, and because they are independent, x 1, x 2, etcetera is a sample of which has actually occurred, and therefore, we obtain the likelihood function as product of f of x 1 into f of x 2, etcetera, for those parameters theta 1, theta 2, etcetera. So, we first define the likelihood function as product of f of x I theta 1, theta 2, etcetera, theta m over I is equal to 1 to n. This is the likelihood function, and we are seeking those parameters theta 1, theta 2, etcetera, which will maximize the likelihood L, which means we are looking for that set of parameters theta 1, theta 2, etcetera, theta m, which results in the maximum likelihood of obtaining this particular sample x 1, x 2, etcetera, x n. That is the principle here. So, we formulate the likelihood function and then we maximize the likelihood function with respect to theta 1, theta 2, etcetera, theta m, generate m number of equations by taking the first derivative, because we are looking at the maximization of L here, maximization of L associated with the thetas. So, with respect to each of the theta I, you differentiate that, equate it to 0, generate m number of equations and solve the m equations to get the parameters, m parameters. So, we just used method of moments as well as method of, we have just introduced the method of maximum likelihood. The maximum likelihood estimates are not unbiased estimates. Remember, we also introduced earlier the concept of an unbiased estimate and the consistent estimates. Maximum likelihood estimates are not unbiased. However, as you estimate using maximum likelihood methods with several samples, large number of samples, then they may be asymptotically unbiased. So, it may be shown that the maximum likelihood estimates are asymptotically unbiased. However, the maximum likelihood estimates are consistent. So, we just introduced the consistency concept. So, the maximum likelihood estimates are consistent. Method of moments and maximum likelihood, method of maximum likelihood do not always produce the same estimate of false parameters. So, this must be remembered, that is, you may use method of moments, you may come up with some estimates for the parameters, but when you use the method of maximum likelihood, you may come up with some other estimates for the parameters. When this happens, the maximum likelihood is generally preferred over method of moments. So, the maximum likelihood estimates are generally preferred over the method of moments. Let us take a simple example to demonstrate how we estimate the parameters using the method of maximum likelihood. So, we will again take the same example as the exponential distribution as we consider for the method of moments. F of x is equal to lambda e to the power minus lambda x. So, the parameter is lambda here. So, we formulate the likelihood function L of lambda is equal to lambda e to the power minus lambda x 1 into lambda e to the power minus lambda x 2, etcetera. So, essentially what we do is we formulate the likelihood function by putting x is equal to x 1 into x is equal to x into f of x 2, which is by putting x is equal to x 2 and so on. So, this is the product lambda e to the power minus lambda x 1, lambda e to the power minus lambda x 2 and so on, which is written as lambda to the power n, you are multiplying it 10 times, e to the power minus lambda sigma x I, because this will be e to the power minus lambda x 1 plus x 2 plus x 3 etcetera inside bracket. So, this is minus lambda e to the power I am sorry, I will repeat lambda to the power n e to the power minus lambda summation of x I over I is equal to 1 to n. It is often convenient to take the logarithms of this, logarithm of the likelihood function, because logarithm is log of x is a monotonic function of x, and therefore, log of x will have the maximum at the same place where x has the maximum, and therefore, if we take the logarithm of likelihood and then look at that value of lambda in this particular case, at which the log L of lambda has a maximum, the same value of lambda also corresponds to the place where L of lambda has maximum, and we are looking for that particular value of lambda which maximizes the likelihood function L of lambda. So, the log of likelihood will be equal to n lambda n log of lambda minus lambda sigma of x I. We are simply taking the log of this. We differentiate this with respect to lambda because we are looking for the maximum value of log of lambda. Differentiate this with respect to lambda, equate it to 0, you get n over lambda minus sigma x I here, n over lambda minus sigma x I, you are differentiating with respect to lambda will be equal to 0. And from this you get, this is minus lambda sigma x I plus n is equal to 0. From this you get sigma x I by n is equal to 1 over lambda. What is sigma x by n? That is x bar. So, x bar is equal to 1 by lambda. So, we write from this lambda I cap, which is the estimate, will be equal to 1 by x bar. So, this is how we estimate parameters using the maximum likelihood method. Essentially, we formulate the likelihood function, which is simply the product of f of x at x is equal to x 1 into f of x at x is equal to x 2 and so on. So, f of x I for I is equal to 1 to n, because you have the sample x 1, x 2, x 3 etcetera x n. We formulate the likelihood function, then differentiate the likelihood function with respect to each of the parameters theta 1, theta 2 etcetera theta m, generate m equations, equate it to 0, that is the first derivative, equate it to 0 because we are looking for the maximum value. The necessary condition is that the first derivative must be equal to 0, generate m equations, solve the m equations to get your m parameters. So, in this class today what we did is we went on to introduce the type 3 extreme value distributions, and specifically we covered the Weibull distribution, which is used generally for the lower extremes, for example, the minimum values of stream flows and so on. We introduced the Weibull distribution and solved a couple of examples. Then we went on to discuss the parameter estimation. We introduced the concept of an unbiased estimate and also a consistent estimate, and we covered 3 methods of estimating the parameters. One is a method of matching parameters, where we simply look at the sample and estimate certain parameters from the sample and equate it to the we estimate certain probabilities from the sample and equate it to the probabilities as obtained from the theoretical distribution. In the method of moments, we take those many moments as we have a number of parameters and thus generating those many equations, and solving these equations we get the parameters, estimates of the parameters. In the method of maximum likelihood, we define a likelihood function and obtain those parameters which will maximize this likelihood. How do we do this? We take the first derivatives of the likelihood functions with respect to each of these parameters, equate it to the 0, because that is a necessary condition for the maximum of a function, equate it to 0, generate m number of equations when you have m number of parameters and then solve them to get the parameters. So, we continue this discussion in the next class. Thank you.